Quantum technology is promising, but also perplexing. In the coming decades, it is expected to provide us with various technological breakthroughs, smaller and more precise sensors, highly secure communication networks, and powerful computers that can help develop new drugs and materials, control financial markets, and predict the weather much faster than current computing technology ever could. To achieve this, we need so-called quantum materials, substances that exhibit pronounced quantum physical effects. One such material is graphene. This two-dimensional structural form of carbon has unusual physical properties such as extraordinarily high tensile strength, thermal and electrical conductivity, as well as certain quantum effects, restricting the already two-dimensional material even further. For instance, by giving it a ribbon-like shape, gives rise to a range of controllable quantum effects. This is precisely what Michael Perrin's team leverage in their work. For several years now, scientists in Empa's Transport at Nanoscale Interfaces Laboratory have been conducting research on graphene nanoribbons under Perrin's leadership. Graphene nanoribbons are even more fascinating than graphene itself. By varying their length and width as well as the shape of their edges, and by adding other atoms to them, the researchers can give them all kinds of electrical, magnetic, and optical properties. Research on the promising ribbons isn't easy. The narrower the ribbon, the more pronounced its quantum properties are. But it also becomes more difficult to access a single ribbon at a time. This is precisely what must be done in order to understand the unique characteristics and possible applications of this quantum material and distinguish them from collective effects. In a new study published recently in the journal Nature Electronics, Perrin and EMPA researcher John Sang, together with an international team, have succeeded for the first time in contacting individual long and atomically precise graphene nanoribbons. Not a trivial task. A graphene nanoribbon that is just 9 carbon atoms wide measures as little as 1 nanometer in width. To ensure that only a single nanoribbon is conducted, the researchers employed electrodes of a similar size. They used carbon nanotubes that were also only 1 nanometer in diameter. Precision is key for such a delicate experiment. It begins with the source materials. The researchers obtained the graphene nanoribbons via a strong and long-standing collaboration with EMPA's Nanotech at Surfaces Laboratory. The precursor molecules came from the Max Planck Institute for Polymer Research in Mainz. As is often the record for advancing the state-of-the-art, interdisciplinary is key, and different international research groups were involved, each bringing in their own specialty to the table. The carbon nanotubes were grown by a research group at Peking University, and to interpret the results of the study, the EMPA researchers collaborated with computational scientists at the University of Warwick. Conducting individual ribbons by nanotubes posed a considerable challenge for the researchers. The carbon nanotubes and the graphene nanoribbons are grown on separate substrates. First, the nanotubes need to be transferred to the device substrate and conducted by metal electrodes. Then the researchers cut them with high-resolution electron beam lithography to separate them into 2 electrodes. Finally, the ribbons are transferred onto the same substrate. Precision is key. Even the slightest rotation of the substrates can significantly reduce the probability of successful contact. The scientists confirmed the success of their experiment through charge transport measurements. This project enables the realization of single nanoribbon devices not only to study fundamental quantum effects such as how electrons and phonons behave at the nanoscale, but also to exploit such effects for applications in quantum switching, quantum sensing, and quantum energy conversion. Graphene nanoribbons are not ready for commercial applications just yet, and there is still a lot of research to be done.